Hi everyone, my name is Hiroshi Suzuki. Thank you for attending our session, Deep Impact Recognizing Unknown Malicious Activities from Zero Knowledge. I hope you like it. First, let me introduce ourselves. My name is Hiroshi Suzuki, and this is Hisao Nashua. We are from Internet Initiative Japan, that is called for IIJ. For short, sorry. IIJ is a Japanese ISP, and we are the first commercial ISP in Japan. We belong to the CSAT team, IIJ SECT. We are malware analysts and forensic investigators. Next, let me explain what this talk is about. This talk is about detecting malicious activities using deep learning in the absence of matching patterns, blacklists, behavioral analysis, and other indicators. We will cover these two methods, C2 servers detection and exploit kits detection. Next, let me explain about what zero knowledge means. Surely you would agree that you cannot detect anything if you have really zero knowledge. In this talk, zero knowledge means there are no any IOCs to detect malicious activities. You could be relieved from analyzing malicious samples and collecting IOCs by using our methods. This is the agenda of this talk. First, we will explain what is the problem on the existing detection methods and why we do this research. Second, we will give you how to detect C&C servers with CNN models. Third, we will show you how to detect exploit kits with RNN and DNN models. Finally, we will tell you the summary of this talk. Okay, let's take a look at the problems of the existing detection methods and our motivation. In order to detect malicious activities, there are several existing approaches, such as pattern matching, blacklists, behavioral analysis, event log correlation, and so on. But they have several problems. For example, some attacks could circumvent them because information such as malicious domains and IP addresses are frequently and easily changed by attackers. Current approaches can only detect known malware or attack methods as well. In addition, some of the solutions are too expensive for ordinary companies. We want a more reliable and a new approach without incurring any additional costs. This is our main motivation. For another motivation, we want to utilize logs more effectively because they take up so much space, but we rarely use such logs except for during incident response. For example, we only use them for CM in particular cases, anomaly detection, pattern matching when you get IOCs. However, we are concerned to handle logs because the size of them are too huge to analyze. Complex detection rules are too hard to process them. So we decided to use deep learning. But why is it suitable? Deep learning can handle huge samples and many features. It can also recognize patterns automatically. Therefore, we felt it would be a suitable solution for log analysis and help us distinguish between malicious and benign patterns. This is the reason why we use deep learning in this talk. From the next slide, we will talk about how can we detect each malicious activity with the technique? Okay, let's move on to the first detection method, C2 servers detection. First, let me explain why C2 servers detection is difficult. For example, in order to detect them, we need to collect malware samples and analyze them. And even if we get samples and IOCs, attackers will change them frequently and easily. It's like a cat and mouse game. Next, let's think about how to detect C2 servers without any IOCs. Many malware, such as bot or rat, access to C2 servers to get commands from attackers or to send keep alive at some intervals. And typical polling takes place between every 20 seconds and 7 minutes. In this research, we focus on C2 servers of bot or rat. We don't target ransomware C2 servers because that kind of malware often communicates only once or even no communication is occurred. Communication intervals are important for attackers because if they choose a short interval, they will be able to move around freely. However, we will also be able to detect easily by counting the total numbers of the communications. On the other hand, if they choose a long interval, they will be limited to move. But it will be difficult for us to detect the activity because it will be too small numbers of the communications to find it if we sum up each destination host. This is a double-edged sword for them. Sorry. Next, let's take a look at the difference between a benign communication pattern and a malicious one. These two tables show total numbers of communications in every minute for an hour. The left table shows legitimate communications between a benign client and a server. It is rare for typical users to communicate periodically with a legitimate web server for a long time. In contrast, the right table shows malicious communications between an infected client and a C2 server. Since bot or rat communicates at some intervals, you can see a pattern like vertical straight lines on the right figure like this. Therefore, we consider deep learning models are able to recognize the difference between benign and malicious communication patterns. We thought CNN can especially recognize the difference if we can image logs. CNN is a sort of deep neural networks. It is one of the best methods for image classification, and several CNN models are already superior to human beings. That's why we use CNNs for detecting C2 server patterns. In order to use CNNs, we need to convert logs into images. But how do we do that? From the next slide, let me explain about it. A common graphical image structure consists of width, height, and 3 color channels. It means RGB. And a monotone color image has width, height, and a channel. It means grayscale. However, we needed to pick effective parameters for channels since we generated images from logs because they don't have degrees of RGB colors. For example, we can use information such as total number of communications during the time interval, sent and received bytes for channels. Here, let's assume there are 3 logs like this. all communications between 172, 16, 249, 249, 104, and example.com happened at 5:01 a.m. and they occurred 3 times. So they can be converted into a monotone color image if we pick only total number of communications during the time interval as one channel, like this. At this time, we tested 3 patterns of parameter extraction. The first pattern has 3 channels like this. The channels consist of total number of communications during the time interval, averages of sent bytes, and averages of received bytes. The second pattern on the left figure has a channel which expresses total numbers of communications during the time interval. And the third pattern on the right figure has also a channel, but it means communication flags instead of total numbers. And these two patterns got nice results against in-the-wild malware. So we used these patterns to create our models. Next, we also to consider width and height in order to convert logs. We tested these 5 patterns, and the last 2 weren't able to distinguish malicious and benign patterns. So we've chosen the third option, which implies aggregating data every minute for our models at this time because it is the best result against in-the-wild malware. Next, we will explain datasets for training and testing our models. First, let me explain the training dataset. We use over 1.5 million images that are converted from approximately 3.7 gigabytes of proxy logs for benign data. And for malicious data, we generated over 1 million C2-like communications with a simple script. We didn't use any actual malware traffic for training data. That's why we call this method zero knowledge. We will mention this later. Next, let me explain the testing datasets. For benign data, we use approximately 4.5 million of benign images in total that are converted from about 11 gigabytes of proxy logs. For malicious data, we use in-the-wild malware communications from actual incidents such as PlugX, XXMM, Red Reefs, Kins, Dreambot or Asnif, and so on. We used 11 different malware families to test whether our model can detect or not this time. We decided to only use malware families which were communicating with live C2 servers for our malicious test data. This is because the sweeping intervals between cases which received commands from C2 in a normal fashion and ones which did not are different. We prepared these 11 malware families. Next, let me explain how we generate C2-like communication patterns. As we mentioned earlier, we use generated C2-ish patterns for malicious data of the training dataset with a simple script. First, we generated a variety of periodical patterns starting from once in 3 seconds and going up to once in every 3 minutes, building up in 100 milliseconds increments. This script also outputs sparse patterns starting from every 3 minutes and going up to every 12 minutes, building up in 10 seconds increments. We also simulated certain patterns which sleep occurs for several minutes after frequent longer connections to C2 servers, because some malware families have similar patterns. This left figure expresses 2-minute sleep after 2 minutes of activity, and the right figure expresses 3-minute sleep after 3 minutes of activity. In addition, based on the patterns that have been generated so far, we generated more patterns using these two methods, rotation and random noise. This is a rotation process. The left figure is an the left figure is an original pattern, and the right top picture is an example that is rotated a minute from the original one. The right bottom image is another one that is rotated 2 minutes. And we also amplified simulated patterns by changing the number of each column randomly to better resist a CNN attack. The right figure have been cleared 3 columns from the original one. Okay, in this subsection, we will explain one of the best models we created. This is one of our models. We use Keras with TensorFlow backend at this time. This is the core code. As we mentioned earlier, we decided to use 1 hour window, and we use total number of communications during a minute as a channel. As a result, an image has 60 width by 1 height by 1 channel dimension. Firstly, our model has two convolutional layers here, and then it has a max pooling layer. After that, it has 2 convolutional layers again. Then there is a perceptron layer here after flattening. Finally, there is the output layer. It's very simple model, right? Let me explain other training related parameters. We also did these 2 methods to get better results: shuffling the training dataset and feature scaling. And other configuration values that we used are here. And this is the result for training. It is high accuracy as well as low loss rate for both training and validation samples. This figure is automatically generated by Keras. I'm sorry, the legends are overlapping with the actual values. The blue line shows the accuracy of training samples, and the orange line shows the accuracy of the validation samples. Okay, now let me explain the results of our models for testing datasets. First, this is the result of benign websites. It's high accuracy as well as low false positives here and here. We can filter out false positive FQDNs with a whitelist because they are small numbers. Next, for malicious samples, our model was able to detect all 11 malware families. Okay, let's take a look at the result in detail. First, let's take a look at targeted attack malware families. These tables are converted images of project samples that is used by some attack group. In pattern 1, every minute the numbers are either changed from 1 to 8 randomly, or there is a 1 minute long sleep like this. But our model could detect these changes. Pattern 2 is easy to detect because it almost communicates around 100 times every minute. Next, Ashrex used by Dark Hotel. This pattern starts with 9-minute sleep, and it sleeps sometimes for 1 or 2 minutes after 2 times communications in a minute, like this. Next, XXMM used by TIC on the right figure. It almost communicates 3 times a minute, but sometimes it sleeps 2 minutes, like this. The left figure is a pattern of Himawari malware that is used by APT10. It accesses almost every minute and sometimes sleeps for a few minutes after consecutive communications, like this. The right figure is an example of Cheches malware that is also used by APT10. This pattern is very simple because it accesses every 5 or 6 minutes. These are patterns of Eric's malware. The left one shows that it accesses every 3 to 5 minutes. The right one is a bit complicated. It accesses 1 or 2 times in a row. Then it sleeps 1 or 2 minutes, like this. Logedrat is used by Blackgear, and it's written in .NET framework. This malware accesses only every 30 minutes, but our model can detect it. From now on, let's take a look at banking Trojan. First, ASNIF. These are a little bit complicated patterns like this. It connects 2 or 3 minutes in a row, and it sleeps for several minutes, like this. Next, sheet or sheaf. It almost connects every minute. And Votrack, it connects every 3 or 4 minutes, and sometimes 2 minutes in a row. And the last one is Kins. It almost connects every 7 minutes. Thus, our model is able to detect a variety of patterns and malware families. Okay, let's summarize for this section. Our simple CNN model can detect malicious communication with sufficiently high performance. The result for our test datasets is high accuracy as well as low false positives. Against in-the-wild malware, our model can detect all 11 malware families that we tested. To accommodate various patterns, an image size should not be too big. Even though it seems to work well at first glance, there is a possibility that it will not detect if a pattern changes slightly. To rotate a pattern and to mix noise could reduce false negatives. False positive measures are required somewhat. In order to apply real-world environments, you should consider a measure of false positives. For example, Some external websites such as cloud storages, sports news sites, stock markets, and so on might cause false positives because of frequent reloading or accessing. So you need to filter out these websites with whitelist in advance, or you need to filter them out if the same alerts come up from many clients. Okay, that's it for this detection method. Let's move on to the next exploit kit detection.
Okay, from now on, we will introduce our exploit kit detection method with deep neural networks. Firstly, we will introduce some existing approaches to detect exploit kits. One of the most popular methods is pattern matching. For example, URL pattern matching and content pattern matching. This is an actual URL path of rig exploit kit. There are a lot of meaningless parameters and values. And the example below is a regex pattern that we used to detect this URL. It's very complex. Unfortunately, there are some problems in this method. Attackers can change the characteristics of URLs and contents easily. It's because these are not important for exploit kit functions and purposes. Paths and parameters in those URLs are often randomized. Therefore, it's difficult to collect whole patterns of ongoing exploit kits. And attackers also obfuscate contents heavily. Therefore, the pattern matching method is not always successful. Behavioral analysis is another approach to detect exploit kits. Typical sandboxes can detect exploit kits by actually browsing each website. However, there are some problems to this approach. A sandbox requires a lot of web browsers and their plugins for detection. It's impossible to prepare for all of the combinations. Behavioral analysis spends several minutes checking each URL. And some exploit kits could detect sandboxes and could also evade them. Therefore, behavioral analysis does not always work well. This is our strategy. Exploit kit servers send contents in a specific order. First, they send landing pages. Second, they send exploit contents, such as flash exploit and so on. Finally, they send malware payload that is loaded by the exploit. We built models to detect exploit kits with proxy logs by focusing on this specific order. We also try to detect exploit kits with characteristics of URLs at first. From now on, we'll explain the latter method first, then we'll explain the former method. Firstly, we focused on detecting rig exploit kit with deep neural networks. These are examples of exploit kit URLs. Number one, this is an exploit URL path sample of rig exploit kit. Number two, this is Nebula exploit kit. Number three, this is Sundown exploit kit. This may seem unfamiliar. Typical exploit kit URLs have these characteristics. Paths and queries have a lot of directories or parameters. They also consist of meaningless words or numbers. Host names in the URLs have strange TLDs that you don't usually use in your country. They also have long and meaningless domain names. Servers are also located in strange countries. We thought that deep neural networks could learn features of those URLs. In this subsection, we use the term deep neural network as multi-layer perceptron. At first, we try to detect rig exploit kit with supervised learning. That is because Rig exploit kit has been the most popular exploit kit over the last few years, and we have collected many samples to prove our theory. For supervised learning, we converted each line of proxy logs into future vector that has 345 dimensions as shown on the slide. Underlying features could express the characteristics of typical URLs of exploit kits. Next, we built a 5-layered fully connected DNN model to run the vectors. The first hidden layer has 150 nodes. The second and the third hidden layers have 30 nodes. And the last hidden layer has only 3 nodes. And we used RELU as activation in all nodes. And we set dropout as 0.2 in all layers. We trained the DNN model with our training dataset. There are about 2 million lines of proxy logs. We collected them from January to February 2017. They contain about 26,000 positive samples of big exploit kit. After training the model with the training dataset, we tested the model with our test dataset. We found that there are about 2 million lines of proxy logs. We collected the samples in March 2017, and they contain about 4,000 positive samples of big exploit kit. And the test resulted in 99.99% accuracy and 100% precision. However, there are some problems. Sorry. The model could not detect other exploit kits such as Nebula and Sundown, since their characteristics in URLs are very different from Rig exploit kit. The model can detect rand exploit kits only. Therefore, we think that the model is still useful to detect variants and to trace small changes. Unfortunately, URLs of each EK could be dramatically changed because they are not important for exploit kit functions and purposes. Then, we built a detection model that could detect unlearned exploit kits. From now on, we introduce the method focusing on content type transition. As mentioned previously, a typical exploit kit sends malicious contents in this order. When the victim accesses the infector server of exploit kits, the victim receives a landing page first. Then, the landing page leads the victim to download exploit contents. Finally, malware payload is loaded as a result of the exploit. These are the actual URL and content type samples of Rig exploit kit. This is a landing page. This is an exploit content, flash exploit. This is a malware payload. These are the actual URL and content type samples of Neutrino exploit kit. A landing page, a flash exploit, and a malware payload. And these are the actual URL and content type samples of Kaishin exploit kit. In this case, multiple exploit contents are loaded. This is an IE exploit, and this is a Java exploit. The order is different when benign servers send contents. In the case of commercial large services, they typically prepare dedicated servers for each content type. For example, one for static text content such as HTML, CSS, JS, and so on. Another for graphic content such as JPEG, PNG, and so on. In the case of small services and private websites, they usually prepare a single server for all content types. Therefore, multiple contents are sent from the same server. We thought that we can distinguish between these benign contents order and exploit kits 1. So we focus on content type sequences. Also, those sequences are strongly related to exploit kit's fundamental functions. They cannot change the sequence pattern easily. Therefore, we thought it's possible to detect exploit kits by checking content type sequences from each web server with recurrent neural network. Recurrent neural network is a type of artificial neural network. It's typically used to process natural language and time series data, such as audio waveform and video stream. In recurrent neural networks, each output of a hidden layer node is used with the next data in a sequence again. It enables RNN to remember its status in relationship to the previous data. Thus, RNN can recognize the order of contents in each sequence. To parse proxy logs with recurrent neural network model, we converted proxy logs into future vector sequences in these ways. We also set the length of each sequence as 5. Firstly, we split proxy logs by destination hosts. Then, we converted each of them into one sequence. These logs split into these 4 sequences. Secondly, we reduced each sequence to enable the RAND model to be tolerant of noise. When lines containing the same content type are continuous, we omitted the second line and all of the following lines containing the same content type. We also omitted the 6 and any future lines because the length of sequence was set at 5. Finally, we converted each line into a future vector that has 84 dimensions. The first 83 dimensions express a content type that was converted with one hot encoding. And the remaining dimension is a flag if a URL and a referrer contain the same domain or not. Next, we built LSTM model with Keras as shown on the slide. LSTM is an abbreviation for long short-term memory and is a type of recurrent neural network. We also tested other RNN models such as simple RNN models and gated recurrent unit models. We found that LSTM models worked better than others in this case. Our model has 3 LSTM layers to recognize the sequence. We trained the model with these 2 datasets. One dataset consisted of benign sequences. We gathered about 578,000 of benign sequences from about 4 million lines of our proxy logs. The other dataset consisted of pseudo-malicious sequences that we generated. We generated about 303,000 exploit kit-like sequences that have characteristics as shown on the slide. These are examples of generated content type sequences. A is a typical sequence. B is a case that the exploit succeeded twice. One is included in a landing page, and the other is a typical flash exploit. C is a case that multiple exploits are loaded. And D is a case that an exploit failed. In the following slides, we explain the tests and the results. We tested the model with malicious sequences that consisted of actual 14 exploit kit traffic, such as Rig, Nebula, Terra, and so on. Then, the model could detect all of them. These are examples that the model successfully detected. Sequence A is a Rig EK sequence. That is very typical. B is a Nebula EK sequence that the exploit failed. This sequence ends without payload. C is a neutrino EK sequence. This is one of the popular patterns of neutrino. And D is a Kaishin EK sequence. It contains multiple exploit contents and a landing page is loaded twice. It also ends without payload. We also tested the model with benign sequences other than the ones we had used in the training phase. We used three benign datasets. Each of them had around 570,000 sequences that were gathered from about 4 million lines of proxy logs. We collected the logs in May 2017, and the test resulted in 99.88% accuracy. And we could reduce the number of false positives into half by applying a simple whitelist that contains only 15 domains. We can also reduce false positives with applying host reputation, anomaly analysis, automated sandboxes, and manual analysis. In this section, we can detect unlearned exploit kits with our LSTM model. It's likely to detect brand new exploit kits. We can also detect learned known exploit kits with our DNN model. It's effective to trace variants of known exploit kits. Okay, let me summarize this talk. Our simple CNN model can detect malicious C2 communications with sufficiently high performance. And our LSTM model can detect unlearned exploit kit traffic. And I'll explain soundbites for our presentation. First, we provided practical ways to detect malicious activities. Second, we gave you several new techniques for utilizing logs of ordinary devices. Third, we disclosed all parameters to detect malicious activities, and attendees are able to reproduce them. Okay? That's it for our presentation. Any questions? Thank you very much.
Thank you for the presentation. You had a very high dimensionality with 84, I think, features in your vector, and you also you had some very specific number of layers and for your deep networks. Did you experiment with different values to see if you could get away with fewer features or fewer layers?
Yes, we tried several layers, and we use different patterns of layers, and we tried some, but not more. So we could raise the accuracy of the by changing the models. But at this time, we would like to show you the results of very small models because we can use it without GPUs, or we can only use CPU.
Hi, thanks for the talk. Referring to the C2 communication detection, first of all, were all of the 11 malware in the training set that you detected? You mentioned that you detected 11 types of...
This one? No.
Is that the... Yes, as in, were those in the training set? Those communication?
Yeah, we don't include We didn't include the actual malware families
Okay, I
in
see. I
training
see.
data.
Yeah. Okay.
Yeah.
Yeah. So, well, my question, because at least at the end you mentioned you had to whitelist some domains because, as far as I understand, you're detecting for basically consistent periodic communication, which can happen with legitimate servers as well. And I wonder if you were able to identify any unique characteristics of malicious, consistent periodic communication as opposed to legitimate ones. For example, beaconing to a mail server versus.
Sorry. Could you give me a simple question?
So basically, what I'm looking for is, are there any characteristics of the communication between all of these families of malicious malware that are unique to those rather than legitimate periodic communication? Be- Because I understand you're detecting periodic communication using this model. And that's why you end up having to whitelist things, because periodic communication can happen with legitimate.
Your question is, do we use the legitimate samples in training data set, right? No. I'm not sure the question.
Sorry. Yeah.
理解しますか
Confusing.
Talk to you later. Okay.
And then, sorry, one quick question also would be, would you be able to use the same method for without separating per server? So at the moment you're separating at the proxy per server, external server. So if you combine them, would you be able to find a pattern within the signal? For example, if the malware is communicating to multiple endpoints at the same time.
Multiple C2 servers.
Yeah, multiple C2s. Yeah. C2 servers.
Several samples used multiple C2 servers, but many of malwares, once they connected, they could connect it. It could connect it. It used only one C2 server.
Okay, once.
So we can get the same results, but if they use round robin or something, then it's a little bit harder to detect the sample, of course.
All right, thanks.
Are you using your models in practice as you are from an ISP? Are you using it? And what's the cost associated? Because it's not only the training, it's the interesting thing is that at runtime, how efficient can you kind of check the classifiers?
Oh, sorry.
使ってるかですよ。
Your question is, we are using this method in real environment? Or
Yes.
not? Okay. We are testing the method right now, and yeah, so far it's good result. Is it you are correct?
Now implementing でいいんだよね。
Now we are testing.
あ、テスティング、テスティング。
Okay. Thank you for coming our session. And that's it.
Thank you.